Welcome to the deep dive. This is where we take complex technical documents, sort of strip away the dense academic language, and really try to bring you the core insights that matter.
That's the plan.
And today we're diving into something that honestly sounds pretty straightforward on the surface. Laser welding. Specifically, laser transmission welding for polymers and advanced composites.
Yeah, it seems simple, right? You've got two pieces, you shine a laser, things get hot, they melt, they stick together, done.
Exactly, like a high-tech hot glue gun.
Something like that. But, the technical sources we've been looking at paint a very different picture. Achieving a really strong, reliable bond, especially in these high-performance materials used in demanding applications, it's governed by incredibly specific, really nuanced physics and molecular science.
We're talking down to the level of individual molecules moving around.
Absolutely. It's about mastering the physics right down to how these long polymer chains behave.
Okay, so we're drawing on technical papers, research that really explores that deep interaction between the laser light and the material itself. We're not just talking about surface melting here. Our goal really is to understand the exact science needed to get that perfect, strong molecular bond, the kind that holds up under serious stress.
Right. So our mission for this deep dive is to get way beyond that just melting plastic idea. We need to uncover, reveal the three big interconnected challenges that engineers have to juggle simultaneously.
Three challenges. Okay, what are they?
First, there's the fundamental molecular science, how these polymers actually stick together, the adhesion part. Second, managing the energy, the physics of heat, how to keep it confined where you need it without causing damage.
Yeah.
That's a huge one for polymers.
Okay, molecular science, energy management.
And third, the laser itself, the geometry of the light beam, how you shape it and control it to deliver that energy perfectly. It's not as simple as just pointing a standard laser beam.
Right, because the wrong shape could ruin everything. Okay, before we jump into the deep theory, maybe let's ground this with a specific example, something about the equipment.
Good idea. The source is often mentioned using a laser diode, pretty common type, specifically operating at a wavelength of 0.9400 micrometers, or 940 nanometers.
Okay, 0.940 nanometers.
And the power.
Typically, the maximum power might be around, say, 46 watts. Which, probably sounds surprisingly low to anyone familiar with metal welding where you're talking kilowatts sometimes.
Yeah, 46 watts seems tiny if you're thinking about melting big chunks of material, especially for things going into aerospace or medical devices. Why so low?
And that's actually a critical point. It gets right to the heart of transmission welding. The trick is, the first layer of polymer you're welding is chosen specifically because it's transparent, or at least highly transmissive, to that 0.940 manometer laser wavelength.
Transparent. So the light just goes straight through it.
Almost all of it, nearly the entire laser power, that whole 46 watts, passes through that top layer without really heating it up much at all. Okay, so the energy isn't absorbed until it hits the interface with the second piece.
Exactly. The second layer, the absorptive layer, is usually designed to absorb that wavelength. Often it contains something like carbon black, or it might be their reinforcing fibers in a composite that do the absorbing.
So you get this really focused, localized heating right at the joint, precisely where you need the bond to form.
That's the beauty of it. It minimizes heating the bulk of the material, reduces stress, prevents warping. It's incredibly efficient energy use.
But it demands extreme precision.
Ultra-precise control. And that precision, that control, is really the crux of this whole deep dive. How do you achieve it consistently?
Okay, let's unpack that first big challenge then, getting the bond itself.
Yeah.
When we weld polymers this way, it's not like using a screw or a bolt, right? No mechanical fastening.
Yeah.
And it's not quite like glue either, not just chemical adhesion on the surface.
No, the success, the real integrity of that joint, relies entirely on achieving what the research calls interfacial healing.
Interfacial healing sounds almost biological. What does that actually mean at the molecular level?
That's the core science, really. If you just melt the surfaces and press them together, yeah, they'll touch. You might get some weak adhesion, but you won't get the full strength the material is capable of.
Not structural strength.
Right. Strength requires actual healing, where the original boundary between the two pieces essentially disappears, becomes one continuous material again. And the model that really describes this, the phenomenon of self-adhesion and what dictates the final mechanical strength, is called reptation theory.
Reptation theory. I remember you mentioning it sounds like snakes.
It does, and it's actually a perfect name. The theory, which was formalized by Pierre-Gilles Lejeune back in 1979, he won a Nobel Prize for his work on polymers and liquid crystals. It models how these incredibly long, tangled polymer chains can essentially snake their way or reptate across the interface.
Like spaghetti strands weaving together.
Exactly like cooked spaghetti. Imagine trying to get strands from one side of the bowl to really tangle up and interweave with strands on the other side. That's a goal.
So just melting isn't enough. Those long macromolecular chains, they need to physically cross that original boundary line and get tangled up in the chains on the other side, like forming a really strong knotted network.
Precisely. The final strength of the weld is directly related to how much entanglement you achieve, how far those chains interpenetrate. And reptation theory lays out 3 key stages for this. Stages that depend critically on both temperature and time.
Okay, stage 1, let's say we heat it a bit, but it's still too cold for major movement.
Right. The chains are still pretty rigid, maybe vibrating a bit more, but not really mobile.
Yeah.
What happens at the interface?
I guess they just touch end to end, maybe?
Correct. You get physical contact between chain ends, maybe
Mhm.
some very weak secondary forces, like van der Waals forces. But there's no real diffusion, no mixing across that boundary,
Yeah.
no structural integration. If you put any stress on that joint,
It fails instantly, right at the original line.
zero strength. Like
Yeah.
trying to stick 2 cold, stiff garden hoses together just by pushing them end to end.
Okay, so that's useless. Stage 2 then, we add more heat. The material softens, maybe gets close to or just below its real melting point, or its glass transition temperature if it's amorphous.
Now we're getting somewhere. Things start to get wiggly. Shorter chain segments, maybe loops, or the ends of longer chains, gain enough energy to actually start moving, diffusing a little bit across that interface.
So some minor penetration.
Some minor penetration, yes. But the main long backbones of the chains are still mostly trapped in what the theory calls their tube, basically, the constraints imposed by all the neighboring chains around them. So the interpenetration distance is still pretty small. The joint might have some strength now, but is nowhere near what the original polymer can handle.
Okay, but the real prize is stage 3. This is where we get the joint to be as strong as the parent material, right? Maximum strength, complete healing.
This is the complete healing phase. And this, honestly, is the big aha moment for anyone trying to do this properly. It requires 2 conditions, not just one. They have to be met at the same time.
Okay, condition 1.
Temperature. The material has to reach, or ideally slightly exceed its melting temperature, TChef, or glass transition temperature. This gives the chains enough energy to really start breaking free from some of those constraints, to become properly mobile.
Makes sense. You need it fluid enough to move. And the second condition, you mentioned this is often missed in quick processes.
Time. Absolutely critical and often the killer. The material has to be held at that elevated temperature for long enough to reach what's called the reptation time.
Reptation time. So that's the time needed for the chains to do their snaking thing.
Exactly. It's the characteristic time required for those long chains to fully wriggle or snake their way out of their confinement tube, cross that boundary, and deeply penetrate into the network of chains on the other side.
Huh.
To achieve that full entanglement.
Hang on. So if I heat my polymer, I hit the melting point perfectly, but then I immediately cool it down, the weld might look okay maybe, but if I didn't give it that reptation time...
The bond will be fundamentally weak. That's the critical takeaway. You rush it, you get a joint that might look visually fine, maybe even homogeneous, but it's structurally flawed. Test it mechanically, and it'll snap right at that original interface.
Because the chains didn't have time to cross over and tangle properly?
Precisely. Engineers measure this using something called the mean square diffusion distance of the chains. If that distance hasn't reached the necessary threshold for the specific polymer, you don't get full strength. Complete interfacial healing means that diffusion distance is substantial, the entanglement is complete, and the joint strength is fully recovered. The interface effectively vanishes under stress.
Wow. That completely reframes the challenge, doesn't it? It's not just about hitting a temperature. You're fighting the inherent sort of slowness of these giant molecules moving. You have to keep the joint hot enough, stable enough, for long enough for the molecules to finish their slow motion ballet.
It demands molecular patience, engineered patience, and that requires incredibly precise energy delivery over time, which leads us straight into the second major challenge. How do we actually manage that energy? How do we keep it hot enough for long enough without just burning or degrading the material while it waits?
Okay, so we need time and temperature for that molecular reptation dance. Now, how do we deliver the energy Q to get that temperature and keep it there right where we need it? This sounds like a major engineering headache, especially with polymers. Let's start with the basics. How does the laser actually heat the material?
Right, so laser energy is carried by photons. We established that. These are massless quasi-particles zipping along at the speed of light. When a photon hits that absorptive layer at the interface and gets absorbed,
Its energy gets transferred?
exactly, that energy transfer excites the atoms and molecules in the polymer, makes them vibrate more vigorously, and that increased vibration, that kinetic energy, is what we measure and feel as temperature, heat.
Okay. And the total amount of heat energy, Q, we need to pump in, isn't the same for all plastics, is it? It depends on the material itself.
Correct. It depends heavily on a property called the specific heat capacity, usually denoted as C.
Specific heat capacity, C.
Yeah, it's basically a measure of how much energy you need to put in to raise the temperature of 1 unit of mass of that specific material by 1 degree Celsius, or 1 Kelvin. It's often measured in joules per kilogram Kelvin. Some materials just soak up more energy for the same temperature change. They have a higher C.
And our sources mentioned this really impacts the energy budget for welding. Can you give an example comparing different polymers?
Sure. Let's take two common ones. Polyethylene, PE, like in milk jugs, and PVC, polyvinyl chloride, used in pipes and things. Generally, polyethylene has a higher specific heat capacity than PVC.
Higher C for PE.
Right. So let's say you want to heat up the same amount, the same mass, of both PE and PVC from room temperature up to their respective melting points. Because PE has a higher C, it's going to require significantly more total energy, more joules, to reach its target temperature compared to the PVC.
So if you're running a production line and you switch from welding PVC parts to PE parts, you can't just keep the laser settings the same.
Absolutely not. You'd have to completely recalculate and retune the energy delivery, maybe increase the power or increase the interaction time, or both, to account for the fact that PE just needs more energy input to get hot.
If you didn't adjust, you'd underweld the PE.
Or completely scorch the PVC with the same settings. It's a fundamental property you have to account for right from the start.
Okay, so that's getting the heat in. But then there's the issue of where the heat goes once it's generated. And this seems to be a massive difference between welding plastics and welding metals. The thermal dilemma, you called it.
Yeah, this is where things get really interesting and often quite challenging. Think about metals, steel, aluminum, copper. What's a key thermal property they all share?
They conduct heat really well.
Extremely well. Very high thermal conductivity. So if you inject heat with a laser or a torch into one spot on a piece of metal, that heat spreads out very quickly, very efficiently throughout the bulk of the material.
Which means the area affected by the heat affected zone, or HAZ, tends to be relatively wide, kind of diffuse.
Exactly. The heat doesn't stay put, it dissipates rapidly. Now, contrast that with polymers.
Polymers are generally insulators, right? They don't conduct heat well.
Terribly. They have very low thermal conductivity, often several orders of magnitude lower than metals. So when you use that laser to generate heat right at the interface,
It stays there.
pretty much, the heat remains intensely confined right near where the laser energy was absorbed. It doesn't spread out easily into the surrounding material.
Okay, so on one hand, that sounds like an advantage. You're not heating up and potentially warping the whole part.
That's the upside, definitely. Much less bulk heating, less thermal stress on the component.
But the downside must be that your control over that localized heat has to be incredibly precise, because the heat doesn't naturally smooth itself out. If you put just a tiny bit too much energy in one spot,
It stays there and cooks the material. It drastically shrinks your margin for error. The risk of local overheating and degradation goes way up.
okay, that makes sense. But let's complicate it even more. Modern manufacturing uses a lot of composites, right? Not just pure polymers, things like carbon fiber reinforced plastics.
Exactly. Thermoplastic composites, especially things like unidirectional or UD composites, where you have continuous fibers, maybe carbon fibers, embedded in a polymer matrix like PEEK. These are high-strength, lightweight materials used everywhere from aircraft parts to sporting goods.
And adding those fibers must completely mess with how heat flows at the weld interface.
It introduces a major factor called anisotropic diffusion. Anisotropy just means the properties depend on the direction.
So heat flows differently depending on which way you measure it.
Precisely. Heat doesn't flow uniformly in all directions anymore. Why? Because the carbon fibers, for instance, conduct heat much, much better than the surrounding polymer matrix.
So if the laser is welding along a path parallel to the fibers,
The heat will preferentially travel much faster along those conductive fibers compared to how it travels across the fibers through the insulating polymer.
the fibers act like little heat highways.
Or sometimes, depending on the orientation relative to the heat source, they can act as barriers or create localized hotspots where heat paths intersect or get blocked, the whole microstructure, how much fiber there is, the volume fraction, and how those fibers are arranged in space directly messes with the effective power you need and, critically, the shape and the size of the actual weld zone you create.
Wow. So welding composites isn't just about the bulk material properties anymore. You have to know the internal architecture.
You really do. Engineers often need complex computer models, finite element analysis, to simulate and predict the heat flow based on that internal structure, just to figure out the right laser parameters. It adds a whole other layer of complexity.
It sounds like mastering this requires understanding the chemistry, the physics of heat flow, and the geometry of the material itself. And given how confined the heat is and how weirdly it can flow in composites, it really forces you onto that processing tightrope you mentioned earlier, which brings us to the absolute limits, the weldability window.
Yeah, that's a perfect analogy. Creating a good laser weld in these materials is absolutely like walking a tightrope. There are two critical temperature thresholds, non-negotiable limits, and you have to stay balanced precisely between them. That narrow thermal zone is the processing sweet spot, the weldability window.
Get it right, you get maximum strength. Get it wrong.
You make expensive scrap, or worse, a part that fails in service. So let's define the boundaries. First, the floor, the absolute minimum temperature you need.
That has to be the point where the polymer actually starts to flow and fuse, right?
Exactly. That's the melting temperature, TA. Or, for amorphous polymers that don't have a sharp melting point, it's the glass transition temperature, TJ. This is the minimum heat needed for the polymer to become mobile enough for fusion to occur and, crucially, for that reptation process, the chain entanglement to even begin.
And if your process doesn't quite reach TF or doesn't stay there long enough,
Failed weld. Simple as that. An unwelded zone. You might just have physical contact, maybe those weak stage 2 bonds we talked about, but no real structural integrity. Total loss of strength right at the interface. That's your minimum energy requirement, and falling short is costly.
Okay, so TF is the floor. What's the ceiling? The point of no return.
That's the degradation temperature, Tc. This is the upper limit.
Yeah.
Go past Tp and the polymer itself starts to break down chemically, irreversibly.
What does that look like? Burning.
You can be charring, yeah, or oxidation, discoloration. You might see bubbling or fumes as the polymer releases gaseous byproducts. The weld bead itself can become non-homogeneous, brittle, and if the energy is way too high or too focused.
You can actually vaporize the material.
Yes, you can get material evaporation, sometimes forming a deep trench or a keyhole right through the weld zone. Obviously, that completely destroys the joint integrity, severe weakening.
So the weldability window is that specific temperature range sandwiched between T-tat, I gotta reach it, and T-tat must not exceed it.
That's the zone. You have to get the interface temperature into that window and keep it there for the required reptation time to get a good weld.
Keep it in the Goldilocks zone, not too cold, not too hot.
Exactly. Only within that window will the weld bead form properly, be structurally sound and homogeneous, and the heat-affected zone around it will be stable and controlled. Stray below, TDEF unwelded, push past TTAT, degraded and brittle.
Now, what really struck me from the sources is how dramatically different the size of this window can be for different polymers. Some seem quite forgiving, while others sound incredibly sensitive.
Oh, hugely different. They offer vastly different levels of processing forgiveness, as you say. Take something common like high-density polyethylene, HDPE.
Okay, HDPE.
Relatively low melting point, easy enough to heat. But critically, its chemical structure means there's quite a wide temperature range between its TF and its TD.
A wide window.
Yeah, maybe tens of degrees or even more depending on the grade. That wider window makes it much easier to control the process. Slight variations in laser power or speed might not push you out of the acceptable range. It's more forgiving.
But then you get to the high-performance engineering plastics, the ones used when failure is not an option.
Right. Think about polycarbonate, PC. Very tough, transparent material used in safety glasses, electronics, medical devices. Or PA66, which is a type of high-grade nylon used in automotive parts, industrial components.
What's different about them?
Well, first, they generally have higher melting points, so you need more energy just to get them hot enough. But the really critical thing is they often have extremely narrow weldability ranges.
Narrow windows. How narrow are we talking?
For something like polycarbonate, the gap between the temperature where you get good chain diffusion, just above TF, and the temperature where it starts to noticeably yellow, bubble, and degrade, PED, might only be maybe 10 or 15 degrees Celsius, sometimes even less.
Wow, only a few degrees between perfect weld and burnt plastic.
It's incredibly tight. Welding polycarbonate or similar narrow window materials, isn't just manufacturing. It feels more like a microsurgery. Any tiny fluctuation, a blip in the laser power, a slight change in scanning speed, maybe an inconsistency in the material itself can instantly push you from the sweet spot right into the degradation zone.
And ruin the whole part, which could be very expensive.
Very expensive. This extreme sensitivity is precisely why engineers couldn't just rely on simple laser beams and basic controls. It forced decades of research into developing incredibly sophisticated ways to shape and control the laser beam itself, especially when it's moving.
Because if you have to maintain that razor-thin temperature window while scanning across a surface, the way you deliver the energy, the beam profile, has to be absolutely perfect. It can't be causing hot spots or cold spots.
Exactly. Which leads us right into the physics of movement and why the standard off-the-shelf laser beam profiles often just don't cut it.
Okay, so hitting that narrow window requires perfect energy delivery. Let's look at the laser beam itself. How is laser energy typically characterized? We mentioned wavelength earlier, but what about how the power is distributed across the beam?
Right. Beyond wavelength, the key thing is the power intensity profile, or spatial profile. How intense is the beam at different points across its footprint? In industrial lasers, you mainly run into two standard profiles. The first one is the most common, the natural output of many lasers,
Yeah.
the Gaussian profile.
Excellent. Like the classic bell curve shape, right?
Exactly like a bell curve. It's got a very intense, high-power peak right in the dead center, and then the intensity falls off smoothly, quadratically towards the edges. Maximum power is concentrated in the middle.
Okay, Gaussian. What's the other standard one?
The other common one is often called a flat top or a top hat profile. This one isn't usually the natural output. It's engineered using optics
Engineered how?
to try and distribute the laser power uniformly across the entire beam diameter. So instead of a central peak, the intensity graph looks flat across the top, like a top hat.
Okay, intuitively, for welding something heat sensitive, that top hat sounds better, doesn't it? Uniform power should mean uniform heating.
That's the immediate thought, yes. Uniform power across the spot seems ideal for avoiding hot spots. Now let's bring in the fundamental physics. The total energy delivered, E, measured in joules.
Is the power, P, in watts, multiplied by the time the laser interacts with that spot, T, in seconds. E equals P times T.
E equals pxt. That simple equation is the absolute core of the problem here. If the laser was just sitting still, shining on one spot, controlling E would be relatively easy. You set your power P, you control your time T, done.
But you're not sitting still. To make a weld seam, the laser has to move to scan across the surface.
And the instant that beam starts moving, the interaction time, key, is no longer constant for every point across the width of the beam path.
Ah, right. Because a point right in the middle of the track gets the full beam passing over it.
While a point near the edge of the track only gets grazed by the edge of the beam for a very short time, exactly, that's the crucial insight. When the laser scans at a certain speed, the exposure time t becomes highly non-uniform across the track width. Any point directly under the center line of the moving beam experiences the maximum possible interaction time, but points out towards the edges of the track, they see the laser for a much shorter duration, receiving minimal interaction time.
So the time component T isn't flat, it actually looks Gaussian, peaked in the center.
Precisely. The interaction time t as a function of position across the track follows a Gaussian distribution. It depends on the beam's diameter and how fast you're scanning. And because E equals pxt, this means even if your power P was perfectly flat, the total energy deposited, E, will still be non-uniform, peaking in the center.
Okay, now let's apply that moving Gaussian time factor to our standard beam profiles and see why they fail for these narrow window materials. First, the standard Gaussian power profile.
Right, so you start with a Gaussian power profile, P, which is already intensely peaked in the center.
And you multiply that by a Gaussian time profile, T, which is also peaked in the center because of the movement.
What happens when you multiply two functions that both peak strongly in the middle?
The result is extremely peaked in the middle. The deposited energy, E, is massively concentrated right at the center of the weld track.
Exactly. That super intense central energy peak easily blows right past the degradation temperature, TD. You get immediate burning, charring, maybe even that keyhole effect we talked about. Instant material damage in the center.
And meanwhile, out at the edges of the track,
The power P was already low because it's a Gaussian beam, and the interaction time T is minimal. So E equal pxt is incredibly low at the edges. So low, in fact, that the material there probably never even reaches the melting temperature, TF.
so the result is a disaster. A burnt, degraded, brittle center and cold, unwelded edges.
A completely non-homogeneous weld bead with terrible overall strength.
Yeah.
Useless. So the standard Gaussian beam is often a non-starter for precision polymer welding in motion.
Okay, so the engineer thinks, right, the Gaussian power profile is the problem. I need uniform power. So they switch to the engineered top hat beam. P is now uniform. Surely that fixes it.
And this is where the subtle physics of motion really trips up that initial logical engineering step. Yes, you now have a uniform power, P, across the beam spot thanks to your top hat profile.
Yeah.
But the laser is still moving, which means the interaction time, T, is still Gaussian, still peaked in the center of the track.
So even with flat P, when you calculate E equals PXT because T is Gaussian.
The total deposited energy, E, is still highest in the center and tapers off towards the edges.
Yeah.
It follows the shape of the time profile.
So the top hat is better than the Gaussian, maybe, but it doesn't solve the fundamental problem.
Exactly. The top hat profile is an improvement. The energy distribution, E, is less sharply peak than with the Gaussian P, but it's still fundamentally non-uniform. You still get that persistent central overheating, maybe not catastrophic burning, but enough to exceed TDAD and degrade the polymer, and you still risk insufficient heating and incomplete reptation at the edges.
Just can't keep the whole width of the weld perfectly within that narrow TFTD window simultaneously.
Correct. This inherent non-uniformity of energy deposition, E, caused by the Gaussian nature of the interaction time T during movement, represents the major limitation of all conventional beam profiles for this kind of work.
So if we're stuck with an interaction time T that's naturally Gaussian because of movement, and we want the final energy E to be uniform, then the only way to achieve that is to make the power profile P deliberately non-uniform in a very specific way.
You've got it. You need to design a power profile that perfectly counteracts the effect of the time profile. That realization, you needed to actively compensate for the motion effect, is what really drove the advanced research in this area. The ultimate goal became clear. You need to achieve a perfectly symmetrical, perfectly flat energy deposition profile, E, across the entire width of the intended weld.
A flat E profile.
Yes, because only a flat E profile guarantees stable thermal behavior. It ensures that every point across the weld width reaches necessary temperature, stays safely between Tf and T for the entire required reptation time, and cools consistently. That's the key to a truly homogeneous high-strength weld.
So to overcome that limitation, that unavoidable Gaussian T from movement, researchers had to get clever. They needed to sculpt the power profile, P, in just the right way. Which brings us, I think, to the really advanced solution mentioned in the sources, the M-shaped beam.
The M-shaped beam profile. It sounds a bit odd, but it's an incredibly elegant solution that came directly out of understanding this P times T problem. The core principle is, if movement naturally creates an intensity peak in time at the center, then our power profile needs to have an intensity dip in the center to compensate.
A dip in the center, so less power right in the middle.
Exactly. Instead of aiming for maximum power in the center like a Gaussian or flat power like a top hat, the M-shaped profile is designed to have two distinct symmetrical power peaks, or lobes, on either side of the beam's central axis, with a deliberate valley or reduction in power right in the middle.
So if you looked at a graph of the beam's intensity when it's standing still, it would literally look like the letter M. Lower in the middle, higher on the sides.
Precisely. The center is intentionally designed to deliver slightly less power intensity. And, critically, the edges or shoulders of the M shape deliver slightly more power than they would in a standard profile. Now, if you didn't know about the movement effect, this M shape might look completely wrong, maybe inefficient.
Yeah, why would you want less power in the middle? But the magic happens when you combine this M-shaped power profile with the movement, right?
That's where it all comes together. You take your carefully crafted M-shaped power profile, P, with its central dip and raised shoulders, and you multiply it by the unavoidable Gaussian interaction time profile, T, with its central peak and tapering edges, which arises from the scanning motion.
And the two non-uniform shapes cancel each other out.
They interact perfectly to normalize the result. Think about it. The lower power intensity at the center of the M shape, P, is applied for the longest duration, the peak of T. The higher power intensity out at the shoulders of the M shape, P, is applied for a shorter duration, the tapering sides of T.
It's like an optical pre-correction for the time distortion caused by movement.
Exactly. The deliberate valley in the power profile perfectly compensates for the natural peak in the exposure time profile. And the net result, the final calculated energy deposition, E equals PXT, becomes remarkably uniform across the entire width of the weld track.
A flat E profile. Just what we needed.
Just what we needed. This uniform energy deposition ensures homogeneous heating. The entire width of the joint reaches the right temperature, stays within that critical TFTD window, and gets the necessary time for full reptation and healing. This is how you achieve consistent, high-quality welds, especially for those tricky materials like polycarbonate with their super narrow processing windows.
That level of control is amazing. But how do you actually create an M-shaped beam? You said it's not the natural output of most lasers. It must require some pretty fancy optics.
Oh, absolutely. This isn't done with simple lenses. It requires specialized optical components. The most common approach uses something called diffractive optical elements, or DOEs.
DOEs, diffractive optics.
Yeah. A DOE is typically a flat piece of optical material, like fused silica glass or maybe a crystal, that has a microscopic surface pattern etched or imprinted onto it. It's not a smooth curve like a lens. It's a complex pattern of ridges and grooves, calculated very precisely.
And that pattern manipulates the light passing through it.
Exactly. As the original laser beam, which might be Gaussian, passes through this microstructure DOE, the pattern diffracts the light, essentially redirecting the photons, modifying both the phase and the intensity of the light waves in a very controlled way.
So the DOE reshapes the beam, forcing the energy to redistribute itself into that specific M pattern before it even hits the workpiece.
That's the idea. The design of that DOE pattern is incredibly complex, involving detailed optical physics calculations and simulations. But the result is an optical system meticulously engineered to deliver that uniform E equals a PXET profile at the weld interface, effectively canceling out the thermal gradient problems that plagued earlier attempts at high-speed, high-precision laser welding. It's a beautiful example of mastering the physics, using light to fight the effects of motion to enable a delicate molecular process. Hashtag tag summary and outro.
Wow, that was quite the journey. We started with what seemed like simple melting and ended up deep in molecular dynamics, thermal physics, and some seriously advanced optical engineering. Let's try to quickly recap the three big takeaways, the key concepts you've hopefully grasped today about making laser transmission welding work.
Okay, first, we grounded ourselves in the fundamental physics of the bond itself, reptation theory. The big insight there was that weld strength isn't just about melting. It's about giving those long polymer chains enough time at temperature to snake across the interface and get fully entangled.
Time and temperature for the molecular dance. Got it.
Second, we wrestled with the critical importance of the temperature interval, that weldability window. It's defined by the floor, melting temperature TEEF, and the ceiling, the degradation temperature TEEF. And we learned that for many high-performance materials, this window can be terrifyingly narrow, making control absolutely paramount.
The tightrope walk. Okay. And
third, we saw why that control demands sophisticated engineering of the laser beam itself. Standard profiles like Gaussian or even top hat run into trouble because of the physics of movement, the solution. Advanced profiles like the M-shaped beam, cleverly designed to compensate for the non-uniform interaction time and deliver perfectly uniform energy deposition, E, across the weld.
uniform E equals a homogeneous, strong weld. So this incredibly detailed, almost surgical level of control over light, heat, and time, this is what enables modern manufacturing, right? Joining advanced materials for aerospace, for medical implants.
Absolutely. This is the science that allows engineers to join complex heat-sensitive components perfectly without causing hidden thermal damage or weakening the material. It unlocks designs and structures that wouldn't be possible otherwise.
Okay, so here's a final thought to leave you with, maybe connecting the fastest and slowest parts of this whole process.
Okay.
We spent a lot of time talking about laser beams, photons moving at the speed of light, literally the fastest thing there is. But ultimately, we discovered that the actual strength, the real structural integrity of that final weld, doesn't depend on the speed of light at all. It depends entirely on that incredibly slow, patient, temperature-dependent process of reptation. The time it takes for those molecular chains to slowly snake their way across the boundary.
That's a great point. The speed of the tool versus the patience of the material science.
So maybe consider this. How often does true success in really high-tech fields, whether it's material science like this or maybe even computing or biotech, hinge not just on raw speed or power, but on understanding and mastering the patience required by the underlying fundamental science? In this case, it's the slow molecular dance, not the lightning-fast laser pulse, that ultimately dictates the strength.
That's definitely something to think about. The slowest step often dictates the outcome.
Food for thought. We hope you found this deep dive valuable.
Until next time.
We'll see you then.